Hello and welcome, people of the internet and programming enthusiasts. In this video, we'll walk through what SQL injection is. SQL injection is the oldest vulnerability in cybersecurity. It dates back to the late 90s when underground hackers from the frack community dubbed it Piggyback SQL. They wrote, and I quote, "We're piggybacking SQL commands onto a command that will work. It can and will go wherever the normal pages /SQL can go." SQL injection is a security vulnerability that allows attackers to interfere with the queries to a database. If a site doesn't properly validate user input, an attacker can insert malicious SQL code into a form field or URL, tricking the database into giving up sensitive information like usernames, passwords, or even full admin access. And I'm going to give you an idea of how it works using Python and SQLite to demonstrate the basics of SQL injection. Of course, SQL injection is a lot more nuanced than what I am about to show you, and this is certainly just surface level information, but this will at least give you an idea of how it could happen in your application. What you are seeing now is a simple Flask application with a few endpoints representing some typical functionality. There is also a database which stores a user's ID, username, and password. Now, let's simulate a very common mistake. Here is a simple but flawed login function. This function builds a SQL query using string formatting with user input. This is unsafe because the user can inject raw SQL code into the username or password. If we enter a username and password into the form and click login, we get a variety of messages depending on the input. However, we can add our own input to gain admin access without a valid password. By adding an apostrophe after the username and a double dash, we get instant admin access. Why is that? Let's take a look at the query itself. By adding the apostrophe, we close the string that was supposed to be the username. When we add the double dash after it, it comments out the remainder of the SQL query, and it is never evaluated. Our query that should be this becomes this instead. This kind of input bypasses authentication because the input breaks the query logic. Let's take it to the next level with blind SQL injection. Say we have a function to see if a user has admin rights indicated by a Boolean value in a table. If we were to provide a username to this function, it returns true or false. If a username matches and has admin set to true. Now let's modify the function by adding an apostrophe to break up our SQL statement and add 1 is equal to 1. So this ends up becoming find someone named admin, or find any user where admin equals 1. That means any admin user will cause the check to pass, even if their username has nothing to do with what was typed. An attacker might use this query to probe for the existence of admin users without needing to know exact usernames or passwords. It is a blind attack because the attacker does not see any results. They infer success/failure based on the return value or behavior. Let's try another blind attack example. We'll simulate some kind of processing with random blob. Let's just say the random blob call is some additional layer of authentication or abstraction that takes place. If we try a random username, we see the response time is almost nothing. However, with a valid username, we can see there's an increased response time. Notice how when we inject our own SQL, the response time is significantly longer. However, this may not always be the case, which is where union-based injection comes in. By using union-based injection, attackers can extract data from multiple queries into a single response. Again, we can use an apostrophe to break out of the string literal and add the union keyword with our own little SQL statement. We will inject a union statement into our login form. Since this particular union statement requires a bit of trial and error, we can try a couple of column lengths. Once we get it right, we can see all the rows retrieved by using this union, including a password. At this point, you change any passwords, but until you know how the password was retrieved, it's certainly going to happen again. Another technique attackers might use is error-based SQL injection. Sometimes SQL errors leak information. An error-based attack exploits this functionality to reveal critical information about a database. If we inject an invalid function call, in this case convert, we will receive a database error. Based on this error, we can then gain insights into the database schema. By Googling this error, we can see that the messaging used in this error is specific to SQLite. Now let's talk about preventing SQL injection. The single most effective technique to prevent SQL injection is using parameterized queries. If we modify our error-based SQL injection example, and instead of passing a raw string to the database, we instead provide a parameterized query, we can ensure that any input is treated strictly as values and not executable SQL. Of course, there are also object relational mappers, which offer a layer of abstraction, as well as the least privilege principle, which states that a database user should only have the permissions it needs. Other useful methods also include sanitizing your inputs and preventing any error messages from being returned directly to users. But that's common sense and probably something you do without even realizing. It's unlikely to happen to you, but SQL injection is still one of the most dangerous vulnerabilities out there. But by using the right tools and practices, you can defend your applications properly. Unfortunately, that's all for now. Thank you very much for watching. If you enjoyed the video, please remember to like and subscribe. If you have any questions or concerns, feel free to leave a comment. Until next time, take care and goodbye.